OK, I think we've had that worked out. Good morning. So I was asked to give a talk today on asynchronous backing. Since this is the most significant evolution of parachain consensus since we launched parachains nearly 2 years ago, I understand it's something that many in the community have been waiting quite a long time for. So I won't bury the lead. We're launching async backing on Rococo very soon. Just give us about 2 weeks to cut a release. So today I'll cover how it works in implementation, how the upgrade will go, particularly from the perspective of parachains and from collators, how async backing will enable our future work on scheduling and scaling Polkadot. But first, the name asynchronous backing is very low level based on the implementation of it. It uses a lot of Polkadot-specific language, which can seem, I think, very inside baseball. So I want to take a step back and really situate what we're doing here in a larger context. So first of all, what is backing, right? So this is a tweet here from, I don't know if this is large enough for you to read, from Ed Felton from Off-Chain Labs. He's one person many might describe the invention of the optimistic rollup to. So he basically says that rollups, and include Polkadot in this, are part of a larger class of protocols that divide what blockchains do into 2 phases, right? At first, they order data and they order state transitions and publish data, and then only later do they verify the correctness of state transitions, right? So in Polkadot, we call the first phase backing and the second phase approval checking. Now, typically, when I'm making comparisons of Polkadot to these other heterogeneous scaling solutions, I'm talking about approval checking, because that's something completely unique to Polkadot that doesn't exist elsewhere. But obviously, today, I'm talking about backing. Backers in Polkadot do 2 things, right? One, they stake on the correctness of a state transition. So if a parachain block is later found to be invalid, 100% of the bond of a backer is slashed. Secondly, they distribute the data. They erase your code and distribute it to the other validators so it can be recovered. And this serves 2 purposes. One, in a very short time frame, the full amount of data is needed to validate the blocks in approval checking. And in a longer time frame, we keep it for about a day. At least the post state is needed so that parachains can build on top of it and continue the chain. Otherwise, it's possible for collators to essentially halt its liveness by withholding that data. Now, what's unique about backing in Polkadot compared to these other 2-phase protocols is that it's enshrined, right? So the term enshrined typically means that something is implemented natively in a protocol instead of on a smart contract level. And this is significant, right? There's really significant technical risk that comes with writing things in a smart contract language and deploying them immutably, and that shouldn't be ignored. But I think, moreover, the really important thing is that backing is enshrined in the staking economics and L1 validator set of Polkadot. And this gives us 2 benefits. First of all, capital efficiency, right? So really, we could allow just anyone to stake on a parachain block, right? Collators could submit their own parachain blocks and with just an equivalent amount of bond, and that would be totally fine from the standpoint of the protocol. I just don't think anyone would do it, right? Back of the envelope numbers right now, I think that Polkadot validators have about $10 million US worth of DOT bonded, all of which would be slashed if any parachain block were to be found invalid. And they're earning roughly $1 million a year by backing all those blocks, as well as building relay chain blocks, participating in grandpa consensus, and eventually approval checking as well. Whereas a parachain lease is, I think, averages out to about $1 million locked. That's about $100,000 a year in opportunity cost. So there's great capital efficiency by essentially outsourcing that to someone who's already staking on Polkadot. The second thing is censorship resistance. So backers really have no relationship to the data in a parachain block, right? They're not endorsing it. They're assigned to it randomly. And they're also assigned redundantly. So currently, we have backing groups of 5. That means 5 validators are assigned to every parachain block, and they're rotated using strong on-chain randomness every block. So We could lower that even beyond, like, to less than 5 in a backing group, and that would still mean you have a relatively low chance of an individual backer censoring a parachain block once, and it's essentially mathematically improbable that they would create a significant liveness problem. So these are things that I think are really unique to Polkadot about this first phase backing step. OK, so next to the title of my talk today, asynchronous blockchains. I want to make the case that you'll hear the term modular thrown around so much this year, right? This is, I think, the kind of term du jour in at least scaling in cryptocurrency this year. More specifically, a modular blockchain is when the ordering and data publishing are done on different networks, right? Now, I would argue there's not really a benefit of doing that way, and it's more based on a very particular case that a lot of people developing off-chain solutions have, where they are developing a off-chain network specifically to scale transactions in a native currency that is issued by a network that has very low data bandwidth, Ethereum, right? So Ethereum has something like only a little upwards of 200 transactions per second worth of data bandwidth if it's all published on chain. Polkadot data bandwidth is far from our current bottleneck. I think if it was, it would be somewhere around literally 1,000 times that. I back the envelope. Now, those are not one-to-one because it's based on the different sizes of transactions on each network. But my claim is it doesn't really make sense to separate those. And so a more general term for blockchains that just exists in 2 phases, one of ordering and data publishing, and only later verifying correctness, is asynchronous blockchains. OK. As I mentioned, this really makes sense for parachains because unlike many rollups, they're sovereign chains, right? They're not. We often refer to Polkadot as a sharded protocol because we divide the validator set into committees. But the parachains themselves are not shards of the relay chain, and they're not designed to trade dot. They can't settle their tokens to the relay chain. They're really sovereign chains that just choose to outsource this consensus for the purposes of ordering availability and state transition correctness to a pooled validator set. I've discussed the benefits of that specifically from backing. But for this to really be the case, they have to be the ones driving the growth of their own chains, right? They have to drive it forward. The parachains can't move in lockstep with the relay chain, right? So this means they have to be able to submit blocks to backers whenever they want, build on whatever ancestors they want. And this is really what async backing does. So this is a graphic that I stole from an engineer on my team. It describes async backing mainly from the standpoint of a parachain collator. This is something called pipelining. Pipelining is a general block production optimization that we see in many contexts across the industry. Essentially, when blocks are created in advance of them being included, what we call in Polkadot on the Cumulus side the prospective parachain system, right? So here you see currently on Polkadot, I said the backers do 2 things, right? They stake on and include a parachain block in the relay chain, and they later distribute the data. So this takes 2 blocks, right? So you see here a parachain candidate, so a parachain block that's not yet been finalized, takes 2 relay chain blocks. And this is why we currently have 12-second block times, right? After asynchronous backing, a parachain, and this is like in the most simplest case, right, where they're producing 1 block to be included every relay chain block every 6 seconds. They're producing the second block before the first one is included in the relay chain, right? So this is the simplest case of what we mean by a parachain being able to move asynchronously to the relay chain, right? OK. And I have a thought experiment here that kind of got me to the idea that this is part of a general class of asynchronous blockchains. I got into an argument with Rob about does time to finality increase after asynchronous backing? Time to finality from the standpoint of a parachain. I think it really depends on when you start counting from, right? Now, if you start counting from the time when a parachain block is included, then no, it's exactly the same, right? But I think that's perhaps not the right time to start, right? If a parachain is its own sovereign chain, we should start counting from the time when a parachain block is what we call pre-sealed, or when it's sealed by the parachain collator's pre-consensus mechanism, right? So this can be with the initial iteration of async backing will probably be about 6 to 12 seconds before relay chain inclusion. And so that time to finality does increase by 6 to 12 seconds, right? So I think that really defining parachains as asynchronous blockchains means starting from the time that they construct a block, right? And ideally, that's also the time that it matters for a user. Assuming they're not waiting around in the mempool due to congestion, which shouldn't be the case with this feature either. OK, so practically, we do have to constrain the level of asynchrony for parachains due to load on the relay chain validators. So we're introducing 2 new parameters with this feature. Maximum candidate depth. This refers to the number of parachain blocks that a collator can produce ahead of time. Initially, this will be set to 3, but really it should be parameterized per core, right? So we have an idea coming in the future, elastic scaling, that a parachain can use more than 1 core at once. And with that, so the idea is it should be essentially a segment of 3. And if, say, you're using 2 cores continuously, it should be 6, right? So you're moving then essentially at a velocity of 3. And then secondly, allowed ancestry length. This is the how old the relay chain parent that you're building on is. That the parachain, the parent of the current parachain block that you're constructed, when was it included? So initially we're setting this to 2, but this can be increased indefinitely after just some node optimizations, and it should be because of some scheduling friction, especially as you get into some more exotic scheduling that parachains might take advantage of in the future. OK. So now, as I promised, I'll describe to you what the upgrade to asynchronous backing will look like. And we're preparing a guide for this, so if you're a parachain team or you operate a collator, you don't have to totally pay attention to what I'm saying now. It'll be on the Wikipedia page, and the ecosystem success team can guide you through it. But essentially, first async backing will require a runtime upgrade on the relay chain. Initially, the parameters will be set to 0 and 0, the max candidate depth and allowed ancestry length. That corresponds to synchronous backing, right? So the feature will essentially be live in the runtime, but there won't be asynchronous backing yet. Then we'll have another governance proposal on the relay chain to set the parameters to what we decided are good initial values. And then more importantly, from the perspective of a parachain and a collator, the parachains can first upgrade the runtime. So there are cumulus side parameters that correspond to each of the new relay chain parameters. They can adjust the slot duration. This is how often parachain blocks can be included in the relay chain. Currently 12. They can move that up to 6. And implement this with a new Aura palette that we've written. Only after that, they can upgrade to the new collator that we have designed to work with and generate prospective parachain blocks. This is what we call the look-ahead collator. This is fine. If you do those in the opposite step, the collator just won't compile. So that's not something you could screw up. And then lastly, the parachain runtimes can enable async backing on their chains. And it's worth noting this whole process is asynchronous, right? So parachains and collators upgrade in their own time frame. They'll keep they'll keep collating asynchronously and being included in the relay chain synchronously until then, right? So it's entirely backwards compatible. OK. In terms of the initial benefits of this, one way to look at it is throughput. So generating these prospective parachain blocks gives us a longer authoring duration. That's what we call the amount of time that a collator has to generate a block. Currently a default value we put in Cumulus is 500 milliseconds, right? These aren't hard values from the on the collator side. Really, what we parameterize is on the relay chain side, the amount of work that we want backers to do, the amount of corresponding work we need approval checkers to do, and it's a complex relationship between those. But for collators, really, you just want the backer to not time out at 2 seconds, right? So we decided right now 500 milliseconds, that's a safe value if, think about it, you're waiting for a block to be included, for it to be backed and included, and then that takes nearly a full 12 seconds, and you have a tiny window at the end to construct the next block. and we think 500 milliseconds is safe to reach that. With asynchronous backing, because parachain candidates are generated in advance, really you could push it fully through to the 2-second backing timeout. Maybe a safe value is 1,500 milliseconds, but collators can choose whatever they want, and collators are executing blocks from memory. Validators are doing it from disk, so they should be a little faster. Also, collators aren't required to run the validator reference hardware. If you're, for example, Moonbeam, you're running on Hetzner, you can certainly do at least 2 seconds. Maybe you could push it to 2.5, and play around with what you can get. I've been doing throughput testing all summer on this, and I basically change every Cumulus out of the box is very safe parameters. I basically change all of them to try to get it as fast as possible, and I think you could push that as you desire. Now, also lower latency. Obviously, 12 seconds to 6 seconds, and so together, from the perspective of a parachain, theoretically, that's an 8x improvement in throughput, which is, I think, quite significant just for one, for one feature. Oh, I have half a screen now. OK. But I said more significantly, I think that what asynchronous backing does is it enables us to some of our future work in scaling Polkadot, right? For example, I already mentioned elastic scaling, the idea that a parachain could use 2 cores at once, either because they have that much throughput all the time, or as like a burst condition. Let's say that you're Mythical Games and you're dropping NFTs, and you need to drop, I don't know, 2,000 NFTs in a given block. Then you could purchase an extra core. Instantaneous core time. Say if you're using that to enable elastic scaling with a burst core or for like a high latency chain, that also implies older relay chain parents, right? An older allowed ancestry, just like elastic scaling implies greater max candidate depth, right? But generally in terms of scaling, I think it's important. This is a very overloaded term in the industry, and so I think it's important to say we think about scaling at least in 2 ways on Polkadot, right? What I've been talking about now is scaling throughput, and also scaling the number of tasks, and the specific tasks we're supporting now being parachains. But as you probably heard Gav talking about, we could support many other things. One way that we can scale this is scaling cores, right? So a core is, I think I mentioned this earlier, when you have a backing group, right, and they're performing a function of including a state transition and publishing its data, we refer to that as one core, right? So right now we have one core mapped to one parachain, and this is about it's a metaphor using a multi-core computer. That this is a distributed multi-core computer. It's how we describe Polkadot. Now, the number of cores essentially scales with the number of validators, and to scale validators, there's of course social work required in that. And there's a lot of networking performance work. So roughly what we have right now is 300 validators and about 70 cores we could support, right? And 70 cores, especially with 6-second block times, that's quite a lot, and that's significantly more than we have parachains registered on Kusama. By the end of this year, we expect to be able to support 500 validators and 100 cores. And then eventually next year, our goal is 1,000 validators and 200 cores. And then, if needed, right, and if we were able to have a validator set of many thousand validators, we could even have multiple relay chains and rotate the validators between each chain. So I know that might sound like something sci-fi, but it's kind of based on actually a rather old paper. But that's to say, that would get us in the range there of, upwards, something like 500 to 1,000 cores only. But then, this is assuming one task per core, right? And you might have seen this graphic from Gav's decoded talk, right? These little slices here. So a block is one core being occupied, every relay chain block, and little slices imply multiple tasks per core. So really, one of the ways that we can get the most performance, the most scaling out of Polkadot, both from a throughput and a number of tasks supported standpoint, is by bundling multiple tasks, multiple parachain validation functions, for example, into one core, right? Because cores right now are, from a throughput standpoint, our bottlenecks are number of cores and single-threaded substrate performance, right? So not core capacity. So in other words, the amount of the data that's being that's being distributed across the network to validate cores or to validate parachain blocks. Right now, it's 5 megabytes. That's far from what Substrate can do in 2 seconds, at least with a standard native transaction type. So there's no reason we couldn't even, I think, at the current moment, increase that by like 4 or 5-fold. And if parachains were using that full capacity, that would give us then about a 4 or 5-fold increase in throughput right there. Perhaps more importantly, though, if you look at, I think a lot of throughput numbers are very juiced, right? Also, ecosystems adapt to their throughput capacity. If you look at, Binance Smart Chain, I think at the peak of the bull market, the most number of transactions they did in one block, and they're a very heavily used chain. So I think just shy of 200 transactions, right? And that's the one block peak, right? So that's much lower than after async backing a parachain could do in one block. So even with the current 5 megabyte essentially parachain block size, it would make sense to bundle many parachain blocks doing their essentially with their current usage. To be able to just support more parachains, right? And that's the second metric of scaling I mentioned. The number of parachains essentially that Polkadot can support. And so I'll leave you with this, right? I said just through cores alone, we can almost get to 1,000. And then through increasing the POV size, we can, in bundling cores, we can have maybe even a 5x improvement there. And then if we're thinking the throughput of like an individual, what Substrate can do single-threaded in about 2 seconds, we have a credible roadmap to get Polkadot to support over 1,000 parachains and over 1 million TPS, should we need that, right? Which is pretty far from what we need right now. It's pretty far from what I can imagine anyone in the industry needing. But I guess the message I have is that the design is there, right? And we know how to scale Polkadot through essentially the indefinite future. That's it. Thank you.